Well, welcome everybody. This is going to be a short video hoping to fix some of the horrible things I did on Friday. So let's just get started here. I want to talk about coordinate change for a linear transformation on Rn. First of all, we need to remind ourselves what's the structure of a basis. So a basis on Rn is a linearly independent set which spans. So if I have vector x in Rn, and I can write it as linear combination c1 v1 plus da da cn vn, well, that makes the coordinates of x the column vector with c1, c2, cn, the weights that you need to build x with that basis. That's what we call the coordinates of x. I use the notation x sub beta for the coordinates of x, all right? And notice that by matrix multiplication, we've got the matrix, the basis matrix times the coordinate vector gives us x. So we can solve that for the coordinate vector and we get this lovely formula I've boxed in purple. The coordinate vector is the beta inverse matrix times x. And likewise, we can write x like that. Now we also defined the standard matrix, right? And the standard matrix, let me zoom in a bit here. The standard matrix was defined to be the matrix that you get from plugging in the standard basis like so, and we've seen a few of those, all right? So it's the unique matrix which gives you the formula for a linear transformation by matrix multiplication. And by the way, we say this is the standard basis. As I mentioned in class, if we look at the matrix of the standard basis, we just get the identity matrix, for instance. Now, I think so let me just try to fix things here. And here's the main fix. This is the definition of the matrix of a linear transformation with respect to a possibly non-standard basis. The matrix of T with respect to the basis is the matrix of coordinate vectors of the basis with respect to the basis. I think I wrote this in class Friday, but I certainly didn't emphasize it as the definition. This is the definition for us. So here it is. Definition. Okay. And as such, now I can prove things about this matrix, show you how it works. All right, in order to do that, I first need to prove a lemma, which we should have proved like a class or two ago, probably. Well, I don't know when, but at some point we should prove this. These things are easy to prove, but they should be stated, and here they are. So and I'm also using that notation, the phi notation for the coordinate. Why have one notation when you can have two, right? So phi beta of x is the beta coordinate vector of x. So I'm just giving a different notation for the same thing to emphasize that in fact this coordinate mapping from Rn to Rn is in fact linear and homogeneous. So it's a linear transformation, right? It's additive and homogeneous rather. It's a linear transformation. And it sends the non-standard basis Vj to the standard basis Ej. And its matrix actually is just the inverse matrix of the basis. We can prove these things. Here's the proof. So, first of all, suppose x is a linear combination of the basis and y is a linear combination of the basis with weights given by c1 through cn and beta 1 through beta n, the coefficients of the linear combinations. I'm calling those weights. Those are respectively the coordinate vectors of x and y. But then if we add cx plus y, we can easily work out that the coefficients of the basis are cc1 plus b1 all the way out to ccn plus bn. And then by the definition of coordinate vector, the weights that appear next to the basis, those coefficients are the coordinates of that vector, which gives us the coordinate vector of cx plus y is cc1 plus b1 ccn plus bn. And then through the usual vector arithmetic in Rn, we can rewrite that as a scalar multiple of the c vector plus the b vector, which is then translating back into my formalism here, c times the coordinate vector of x plus the coordinate vector of y. This proves claims 1 and 2 up here. Claims 1 and 2 were just that, written in the other notation. And then for 3 is very silly. If you expand Vj as a linear combination of the basis, you just put a 1 next to the Vj and zeros elsewhere, but that means the coordinate vectors is 0 with a 1 in the jth spot and zeros elsewhere, but that's nothing more than Ej. So this is another way you could define the coordinate map. The coordinate map is the map that sends the non-standard basis to the standard basis. That defines the coordinate map, actually. Now, and then finally for step 4, we already worked this out, but here's the calculation again. X is equal to, the basis matrix times its coordinate vector, which then if you solve for the coordinate vector gives you the inverse basis matrix times X, and that's it. And of course, once you see that formula, that implies the standard matrix of the coordinate map is the inverse basis matrix. Great. What else can we say? Well, glad you asked. So we can prove this proposition here. And so I said this was the definition, I think, in class originally, but let's say that this is not a definition, this is a derived consequence. Here's how it's derived. So t beta beta times the coordinate vector is equal to the coordinate vector of t of x. To prove this, I write x as a linear combination of the bases. Of course, that means the weights are the coordinates of x. Then I use linearity of t to pull out the sum and the constants. Then I use the linearity of phi to pull out the sum and the constants. So that's by the lemma. And then, okay, so this is exactly the coordinate vector of t of vi with respect to beta, which then, if you go back to our basics of how matrix multiplies, is nothing more than this matrix right here times that. Sorry, my phone has decided to be noisy. Times that coordinate vector. But hey, that's exactly what we were trying to prove, that the coordinate vector of t of x is the matrix with respect to the basis times the coordinate vector with respect to the basis. And of course, this straight away gives us a theorem. Well, not straight away, but nearly straight away. This gives us a theorem on how we actually tend to like to calculate. Although any of these things could be used in principle to calculate the matrix with respect to a basis, all right? Anyway, so here we have the theorem that the matrix with respect to the beta basis is the inverse matrix times the standard basis times the basis matrix again. And the proof of that is just this. So my proposition and lemma, the proposition gives me this. But then, since this is the coordinate vector of tx, it has to be the inverse basis matrix times tx, all right? But then, again, using that x is the inverse basis matrix times the coordinate vector of x is the inverse basis matrix times x for the orange to orange, and then green to green. So t of x is the standard matrix of t times x. Now, if this holds for all x in the Rn, it follows then that the matrices are equal, that this is equal to that, which then if you just solve for the t beta beta, you get this lovely formula, which is what we were out to prove. Great. Now, I have a couple of examples to show you how this works. These ones, I'll actually not multiply a 3 by 3 matrix and another 3 by 3 matrix and give you a column vector like in class. Oh my goodness. I guess I'm going to post that video, but I almost don't want to. It's so embarrassing. Goodness gracious. It's the worst. Let's see here. So example 1, if we have this linear transformation and I use this basis 1, 2, and 4, 5, then I can find the non-standard, the matrix with respect to this basis by the calculation below. And so to do that calculation, there's a couple different steps. The one is I have to invert the basis matrix, which is easy enough because this is a 2 by 2. And then, of course, I actually have to multiply out the product here, like so. All right, and you do that, and out pops 0, 2, 3, 0. So, hey, this matrix, this linear transformation, which kind of looks ugly in the original XY, Cartesian coordinate system, it's actually got a kind of nice formula in this non-standard basis. Because we worked out that this is the matrix. Okay, so what does that mean? Well, if we think through it, right, down here, if I let xy be, y1 v1 plus y2 v2, that means that the coordinate vector of xy is y1 y2. And, oopsie, I missed my beta. Whoop, whoop. There we go, fixed. All right. So then, using what I just calculated over there, write it down here. I've got the matrix of t with respect to beta times the coordinate vector equals to that, which means that t of xy is 2y1 plus v1 2y2 v1 plus 3y1 v2, that's what it means to have, to say that the coordinate vector of txy is that, means that t of xy is this particular linear combination of the basis. But if we translate everything into the basis world in terms of v1 and v2, I have that t of y1 v1 plus y2 v2 is just 2 times 2y2 v1 plus 3y1 v2. So if you look at this underlined purple formula right here, it's a far simpler formula than the original one in the Cartesian coordinate system. This is the kind of thing we're after. We want to understand how we can change coordinates on a linear transformation and make it easier to understand and reveal its true nature, its true structure. That's a big theme for the rest of this course. I would point out that you can see the invariance of the determinant and the invariance of the trace in this example. If you look at it, this matrix, it's not obvious, but the determinant of this is actually -6. The fact that the determinant of that is -6 is evident. It's manifest. The trace being 0 is obvious. The trace of this being 0 is also obvious. So there you go. Trace is equal. Determinant equal. Example 2 might be helpful to you guys for your homework a little bit more commentary here about the onto one-to-one issue, right? So here we have a 3 by 3 matrix that I just made up, and I said is t one-to-one or onto. So to figure that out, actually, truth be told, I could just calculate the determinant of this. If we calculate the determinant of this, we'd see that it is 0, and if the determinant's 0, that means the matrix is not invertible, which means that the that the row reduction is not the identity matrix, which tells you that you don't have full rank, right? You don't have 3 columns, so it's not onto. And that also means that there's at least one non-pivot column, which means it's not one-to-one because the null space is non-zero. However, to actually calculate the nullity and the rank, we probably need to do the row reduction in general. And so here's that. A row reduces to this, which tells me that -1, 1, 1 actually is in the null space. That's a basis for the null space. So the null space is one-dimensional. The nullity of this matrix is 1. So it's not one-to-one, it's not onto, but I thought it might be interesting to use a basis which reflects both the range and the kernel. So I made my basis of the matrices, of the vectors, which form the column space and also the null space. So my basis here, because I thought it'd be interesting to calculate, see what happens. Column space basis 1, 2, 3, 0, 2, 2 for A, and the null space basis -1, -1, 1. Now I want to calculate the matrix, of T with respect to the basis, and if I do that, and I tried this twice and got it wrong twice because I was like half talking to people when I did it. Never talk to people when you're trying to calculate the inverse of a 3 by 3 matrix. You're wasting your time. Anyway, so if you do this, you'll calculate eventually that this is the inverse. And so there it is. There's the inverse basis matrix. Now that was a lot harder than what I did in class. In class we had that beautiful orthonormal basis. And to invert it, we just transposed it, right? Oh man, it's so nice. So much nicer than this. But anyway, this is what usually happens. And so then I multiply by, according to the theorem, we're supposed to, where'd it go? Oh man, this right here. Beta inverse T beta, right? So I'm doing that again. So here it is. Oh, it's right here. I just can't read. Duh. And after some calculation, I do this times this, then this is times that. All right. And then that simplifies to this, and then I keep the fractions out front. There's no point in fighting with fractions till the last step. So I ended up with 8/6, 4/6, 0, 5/4, 0. Check that out. So because we put the null space in the last, in the third basis member, it ended up making both the third column and the third row 0. Isn't that kind of neat? I think that would always happen. If you make your basis comprised of like the column space basis and the null space basis, what you're going to get is a matrix which is like 0 in the part of the matrix which corresponds to the kernel. So here's just a little bit more, just trying to understand like what does that formula mean. So we've got v1, v2, v3, So like if x is equal to this, the coordinate vector is ABC. Okay, if x is equal to this, the coordinate vector is y1, y2, y3. So if I calculate t of x, I've got this. By linearity, I've got that. And then using, how do I get from here to here? Well, I use the fact that we calculated the matrix of t with respect to the basis is this. So if the matrix of this is the matrix with respect to beta is this, that means the coordinate vector of v1 is 8, 6, 5, 0, and the coordinate vector of v2 is 4, 6, 4, 0. But what does that mean? That means that t of v1 is 8, 6 v1 plus 5 v2. And this means that t of v2 is 4, 6 v1 plus 4 v2, which then I just put up in here. And of course t of v3 by construction is 0. So in the coordinate system just constructed, here's the formula for t of x. It's just, you know, this plus that, which is, I think, kind of neat. In contrast, here's the formula for t in like manifestly Cartesian coordinates. We put in this, and we get out that. All right. Whereas, you know, this formula is sort of equivalent to this matrix calculation. Not sort of equivalent; it is equivalent. But anyway, I just wanted to show you how to calculate the matrix with respect to the basis and actually not make stupid mistakes. So I hope I've done that. And my apologies again for Friday. So, sorry guys. I think that's it for now. If you have questions about homework, do email me and I will try to help you. So, thanks guys. Have a good weekend.